Okay, everyone, welcome. And next up we have Daniel Nagaj, who will be speaking about very entangled spin chains.
Thank you, Shelby. And today I want to tell you about a couple more examples of things that Lorenza was just telling us about. Got it here about the mic. This is on. This is on. Okay, now we're on. So I'm going to tell you about a couple examples of things that we do which might be fixed points of Lorenza's open dynamics. And this is going to be work that I've been doing with my student Movassagh. And it's a follow-up to work with Shor and Ramis Movassagh and Sergey Bravi about the Wreckage Model that you might have heard. And it's going to be examples of things where the chains and the ground states are going to be really entangled, the right side with the left side, and I'm trying to get as much entanglement as possible. And it's not going to be in classical chains, because classical chains are easy. You can figure out everything in there, the correlations and whatnot, finding the ground states. We're going to talk about entangled quantum chains, specifically for small qubits, specifically for translation invariant chains, which gives us further restrictions, but at least lets us do something, about Hamiltonians that have a unique ground state, and mostly I like it because it's fun to play with. And it's fun because I'm going to be talking about projections and perturbations of Hamiltonians, and together in there I have learned a lot of interesting combinatorics about Motzkin and Dix-Fast, and then founding the gap of this Hamiltonian by looking at conditions of graphs and matchings and all kinds of fun things. So at first, I'm going to discuss entangled chains in general, the area of the gap and entanglement, how they can relate to each other. Then I'm going to give you my big class of constructions where these Hamiltonians are related to some rules that change basis states to other basis states, and then create subspaces of states, where the ground states are going to be unique superpositions over these subspaces, and going to be very entangled. And finally, I'm going to give you a couple more models, which were last week I was here and everybody was very busy with UIP submissions and I didn't submit anything, but I implemented like 3 new models, so I'm going to tell you about those. Okay, so it's going to, with the hope that these models are going to create later a larger family where we might learn something more like in David Gossett's talk about a family of frustration-free translation very possibly chains that are gapless or gap. So it's going to be, my crowning achievement is going to be a pair creation D equals 4, so 4-dimensional qubit model. What can happen in 1 dimension? We know many things, many interesting models in condensed matter. We have the Ising model, we have the Heisenberg model, we know all kinds of things about these. And we have theorems. We know that when the model is gapped, then we have the area law, and we know that the system is gapped. We have an algorithm to find the ground state. In practice, we would not use this algorithm, we use DMRG or matrix product states or more and more inventions on top of matrix product states, and we will find the ground states, figure out the correlations, calculate almost everything that we want. So why am I looking at things? Anyway, because I want to find out whether these types of problems, when I have a chain that's mostly translation invariant, how hard can it be to find the ground state? We do not have a general proof, even for qubits, how hard these things are. And it's interestingly related to the consistency of reduced density matrices, which we know is a general problem, is hard. But what if these reduced density matrices are just on a chain? And what if these reduced density matrices as 4x4 matrices are the same matrix everywhere? And I've been thinking about this with Yikai Liu and Les Reinhardt and recently with Jianxin Chen, because right now we have theorems only about consistency when you can put a matrix and a matrix together on 3 qubits. But what if you are trying to make a chain? We really don't know. And what if the chain is translationally invariant? Right. How examples of chains that are difficult have been made? They've been made by, well, for example, by mapping a computation of a circuit, of a quantum circuit, and a verification procedure into a chain of qubits where like messages get passed around and like qubits are changing. The dimensionality of the qubits is really high, but in the end, the ground state is something like a history state of a computation, where it's I start a computation, I move, I do something, I calculate more and more and more and more. And it's a uniform superposition of states that are like connected like a line. It's clear that I have a state, and I have the follow-up state, and the next state, and the next state. And Hamiltonians that work in there are somehow written in this form. That is always AB is a local state of 2 particles that change into another state of 2 particles. And you can do all kinds of very interesting things already with this simple type of Hamiltonian. And specifically, it's QMA complete when you use like 13-dimensional or 11-dimensional particles, and when you add frustration to it, you can go even down to 8-dimensional particles. Now, we also know that this problem is NP-hard when the ground state itself is a matrix product state with a polynomial size dimension. Then it's in NP, of course, because I can give you the matrix product state. It has polynomial size, and there's a polynomial number of them, and you can calculate things. And when you can calculate things, you can just verify solutions in NP. And what you need is just write your state for these coefficients, rewrite them in terms of matrices, or matrix product states. Now, I could ask then, if I have a state that's a ground state that has a polynomial number, polynomial size matrix product state that already smells like NP. But for that, we kind of still need large dimensional particles in there. So I want to go down again and try to think of like, would we have something more simple? Would we possibly also have like states that are ground states that are somehow natural for QCMA? Or would we make things that would be the fixed points of dissipative models? And I've been also talking a lot about this with Michael Castoriano. And when we restrict ourselves more and more, what happens when we make these models translationally invariant? We know that, again, when the local dimension is very high, you can make QMAX model tiling with Daniel Gottesman and Sandy Rani. And Ramis with folks from Cambridge have been thinking about how to make this model with actually a reasonable number of local dimensions and tiles. So there's a lot to do. But the big question that I have, what is the relationship of the entanglement and the gap in the ground states of translation invariant spin chains? Because when we have a large gap, generally there's almost no entanglement. On the other hand, I would like to have a reasonable gap and a lot of entanglement. And I'm going to present you a couple of models that have this property. And of course, I'm interested in the very limit of where can we possibly go. So, what happens when you have a small gap? When there's a model with an exponentially small gap, imagine that I have a spin chain where these guys really want to be in a singlet, these guys kind of want to be in a singlet, and these guys less and less and less. When you use renormalization techniques, you can show that the ground state kind of looks like singlets that go farther and farther. So it has a lot of entanglement across this middle cut, but unfortunately, the gap of this model is very small. So can we do something where the gap is like 1 over polynomial instead of exponentially small? And yes, we can. And there, even there, in this model, it's kind of like the left side of the chain is going to mirror the right side of the chain. Either we're going to have singlets, or maybe later you're going to see in my models, we're going to have basis states and basis states here that mirror each other. So there was one model where you kind of, the ground state is a history of taking EPR pairs and distributing them, like moving the EPR pair to the left and then moving another EPR pair here across and then creating another EPR pair and so on. And the ground state is a history of all that. And that's been done by Sandy Rani in 2009. And another similar model has been done with synchronized wheels of states by Daniel Gottesman and Hastings, where you have, imagine that your spin chain are 2 squeezed wheels where there are particles that can hop around, so they hop and create entanglement. And then these wheels turn around, and the entanglement can jump out, and then these wheels turn around again and create more entanglement, and so on. The result of these models is that you can get ground states of chains where the entanglement here, in this case for Sandy's model, goes like the gap to the -1/12, and here, where the entanglement entropy goes like the gap to the -1/4. Both of these models have kind of a high local dimension. This one was originally 21, this one was dimension 9, and both are not really translationally invariant. You kind of have to take this model up to n, and then kind of like move it around and around, and then if you look at some point, and then you go farther and farther out, you're going to see more and more entanglement entropy as you're making the block bigger together with the rest, and after some point it will stop. It will have a limit. That's like a native parameter to the block. So we have gaps that go like 1 over some parameter and to something, and we have entropy that grows linear. Let's see what else can we do. Can we make this relationship nicer, and can we make it in a truly translation invariant chain that would not be like just these blocks made out of blocks that are already native blocks, but a very long chain nevertheless, where n would be the length of the chain. I will just take it to infinity. So all in all, we know about these ground states that for 21-dimensional chains or 9 non-translation invariant, the entropy can grow like L. When you have qubits, and you have a frustration-free Hamiltonian, then product state solution, so there's no entanglement. When you have 13 dimensions or 11, you can have a history state, and it can be QMA complete to find the ground state. When you have 8 dimensions frustrated, it's also QMA complete. Then when you have 4-dimensional chains, the ground states can be very, very entangled, and it's for models where Hamiltonians are just random projectors, random rank 4 projectors. David was discussing this. David Gossett's talk, there was a very interesting model where you have rank 1 projector for 2 qubits. Then this is another interesting point somewhere in the sequence where it's rank 4 projectors for 4-dimensional qubits. We really don't know what could possibly happen in there, and it might be an interesting point to look at. Then we have invented the Wreckage Model, which is a really truly translation invariant model where the entropy grows like the log of the length of the chain with Sergei Ravi, the Ramis, Movassagh, Peter Shor, and Movassagh. And then later this model, this was last year's QIP talk, where the bracket model got several species of brackets and the entropy has grown to square root of L. And now my model here is going to be 4-dimensional and it's going to be translation invariant and has the same properties as the 5-dimensional model, but it's going to be different than the brackets, and that's why I want to tell you about it. Okay, so how do I construct all these? I construct these from forbidden states that imply transition rules, and they define invariant subspaces. So for example, let me take the ferromagnetic Heisenberg. This is the Hamiltonian, where this is I plus 1, I plus 1, I plus 1. When you look at that and you do a little bit of trickery with the Pauli matrices, remember that this model, a different model, is particle hopping. This is 0, 1, can go to 1, 0. This type of Hamiltonian, it generates a walk. It can generate like when you have a single particle, it's a walk on a line. Now this can be rewritten as like project to the subspace of 0, 1, and 1, 0, and then flip them. And you can see that this appears in there because this can be rewritten as xx1 minus zz. And then all in all, it's proportional to that model. Somehow this thing is in there. This is 0, 1, 1, 0, 0, 1, 0 with minus sign, and then also can be written out as a projector. So this model generates spins like flipping like this, but also when you look at it, it really kind of forbids the singlet state. So it doesn't like the singlet state. Whenever you have anti-symmetry in your state, then the energy goes up. So I say it punishes anti-symmetry, and it does prefer symmetry. So for example, if I wanted to have a low energy state, and I look at my Hamiltonian and have a state that has some 0, 1 in there, this is going to have some expectation value, so I have to add the same things with the 1, 0, same things with 1, 0, and then I get a 0. Okay? So in the end, my conclusion from this, if you want to have a 0 energy eigenstate, or state, obey the rule. Whenever you have a term in your superposition, apply the rule, change all 0, 1s to 1, 0s, and see where you get. And when you take a superposition of all this, it's going to be a ground state. So how does it look like? Ground state is going to be a uniform superposition over a subspace. Let's look at the subspace. So I hate these states, generates this transformation, and from the state 0, 0, 1 goes to this one, the next one, to the next one. And a superposition over these, which is just a symmetry state, with a single spin up, is going to be a 0 energy state for this model. Okay? Next, if I have 2 1s, this is now connected here. Now the one can jump. Either this one jumps or that one jumps, and they can connect. And this is the geometry of the other subspace. And of course, there's also this subspace, which is all zeros that doesn't move anywhere. It's a zero energy thing. It's really boring. So there will for this model, there's always a completely non-entangled ground state. So that's why I want to have something more, to go beyond qubits so that I can actually do something in there. So, just to sum things up, when I have a forbidden state, gives me a rule of how to change superpositions. These are going to be superpositions over a subspace that are going to be ground states, And I can do Schmidt decomposition to look at how entangled these superpositions are using half-chain invariant subspaces. Because, for example, for states like these, it's zeros here, and 0, 0, 1, 0, 1, 0, or 1, 0, 0 on the right side. Or it's the zeros here, and at 1 here, here, or here. And I do the Schmidt decomposition across the middle, and I see that the rank is 2. And the Schmidt rank of this one is 2, independent of the length of the chain. So my goal now is to create things where the Schmidt rank will be larger. So let's try. To try this, I'm going to invent a new model that's going to be called pair creation. Pair creation means there are particles, the ones, that can move. And if I have a 0, 0, it can go into a 1, 1. So, starting from this model, I can create particles in 3 different ways, create pairs. Now I can have them move. Like here, a 1 moves here, or this is also connected there. And then I can do nothing more but move them again to this state, and then I can create another pair. And that's connected to that state and that state as well. So this is again a geometry of some subspace that's kind of interesting, and it comes from the pair creation model. This one is boring, but wait until you have several times. That's going to be my final one in the end. So I have Hamiltonian, that has some interesting ruling states that are ruled out, creates a geometry, subspace, and the ground state is a uniform superposition over it. Now comes the model that we come up with, that's the bracket model. So the bracket model is now on the 3-dimensional path. It has nothing, left bracket, or a right bracket. The rules, or here are the forbidden states, are a bracket can move, or a bracket can move, or from 2 nothings, a bracket pair can appear. So these are the forbidden states. So let's see what's the geometry of a particular subspace. So for example, start with a well-bracketed subspace. So here, what can happen? What state are these connected to? So I can create all kinds of bracket pairs. Just like this. Now, they can move. Nothing can get created now, so they can move again. And another pair can get created in the middle. This is simple, but wait until you have a chain that's like length 20. It gets really funky. There's another, and there's another pair that can get created in here. Okay? If there's another subspace. There's another subspace with 1 extra bracket. This can move, or move further, and some of them pairs can get created and moved and so on. This is the geometry of the 1 extra bracket subspace for a chain of length 4. And there are some invariant subspaces from which you can get to other subspaces depending on the number of extra brackets that you have. Because extra brackets can get annihilated, so there's just no way that these subspaces will be connected. So what this Hamiltonian does, it preserves well-bracketedness of a state. And this model has very interesting dynamics, which we'll go to, like what the gap is going to be, but it also has very interesting statics, because the ground state itself is going to be a superposition over all well-bracketed states, and it's going to be very entangled. So let's show this. How are well-bracketed states built? Yes, Robert?
Is it a typo up there? You mean open bracket, the middle one in the room? And is it just from zeros or do you also have 1?
Sorry?
Is it just from zeros or do you also have 1?
No, there are no ones. There's zeros, left and right. Three particles. Three. Okay, thank you. So it probably was here as well. Right. I'll change it. So a well-bracketed state, how is it built? A well-bracketed state can be made out of a well-bracketed state combined with a well-bracketed state. Like this one is well-bracketed, this one is well-bracketed, or those ones are well-bracketed, fine. This now corresponds to a superposition over all well-bracketed states of length of half-chain length. Now it can also be made of something with 1 extra bracket and something on the right that has 1 extra bracket. Because now if I delete everything, these 2 extra brackets go together and disappear. Or, like this state can also annihilate with that state. And then, of course, I have 2 extra brackets on the left and 2 extra brackets on the right. And 3 and 3, and so on. And a whole state, a whole superposition of everything is going to be a superposition of all these with superposition of all these, all these with all these, and so on and so forth. I already have the Schmidt decomposition because I now can cut it in the middle, and these lines are going to be different Schmidt states. I just need to normalize them. These lines are orthogonal to each other. They're not orthonormal yet, so I will need to do some counting. How many states are here that are well bracketed on the half chain? How many states are here that are one extra on the half chain, and so on and so forth? But I can do it, make them orthonormal, and calculate the Schmidt coefficients. And it turned out very cool. So we followed up with this. The ground state is the Motzkin state because the states are labeled by Motzkin blocks, which are blocks that start here and here and can go up and down, can go below zero, and can have plateaus as well. And you can divide it in half, and you can see that the Schmidt rank is like n half plus 1. These are uniform superpositions, and when you calculate this piece, you're going to get entropy Schmidt rank n half plus 1, and the entropy that's going to be logarithmic. So it's going to be kind of looks like a critical system without frustration. And the combinatorics are interesting because then you can have like Dick paths are just mountains, just up and down. They are related to Catalan numbers. And Motzkin paths are like Dick paths, except you can have also plateaus. So like this, bracketed state relates to mountains like this, and when you have zeros, you also have like just do nothing and you go up and down. And you can calculate that stuff with Motzkin numbers. And then later in Peters and Ramis' further work, you need to do like colored Motzkin blocks where also like some of these up and down are also have a different color, and then the combinatorics are more difficult, but again, it's doable and interesting. When you have extra bracketed, you start here, you end up at level 1. It's all doable, okay. So there are many significant Schmidt coefficients. Like when you look at this, then the maximums, that's kind of like n squared, square root of n. And when you look at the entropy, it's logarithmic. So it's an interesting model. And the only thing that I need to do is just to make sure that the well-bracketed states are the ground state subspace. Or the ground state lives in the well-bracketed subspace. And you do that by taking your chain and just adding like I hate you and I hate you. And then it means that the energy of all subspaces that have extra brackets will go up. And the only subspace that it doesn't touch is the well-bracketed subspace. So I'll add endpoint projectors. This is not something that I quite like, because then what happens if you're making a chain longer and longer and longer, you still have to have like these two things like at the end, what if they disappear? It should not matter, so it's kind of weird taking the limit to infinity, and we're going to deal with it very soon. And when you do this, the well-bracketed subspace wins, and that's going to be the ground state, and it's a unique, frustration-free, entangled ground state somewhere in there in this model. And I can look, is there anybody nearby that would be not entangled or so? But we show that the gap goes like 1 over a polynomial, and the polynomial the actual one, when we look at numerics, and we cannot really go that far, goes like 1 over a cubed or so. When we actually calculate things, we show 1 over poly, and the poly is a half poly. But in practice, I believe it's like 1 over a cubed, or something similar. We can just show, like what David has shown, that when you have a frustration-free chain, that there's also like an upper bound on the gap. So the gap cannot be somehow like constant. The gap, we can show that the gap is at least like 1 over square root of it, but in fact, like there is even a stronger upper bound on the gap. How do we bound the gap itself? The gap itself is much harder to bound because we have a Hamiltonian that somehow ties Motzkin paths together. So what we do, we make an effective Hamiltonian that works on Dick paths, that erases the zeros. What we do, like we take a Hamiltonian, make one part of it smaller, and treat it as a perturbation, and somehow do something. When I have a Hamiltonian of these Dick paths, I can actually translate it into a Markov chain that has just a nice classical matrix, and then I can do something for the gap of this Markov chain by just looking at the graph congestion or seeing like who's connected to who and how much. And when I know how the things are connected, you can get the congestion from canonical paths, which are paths that, how do I get from here to here? How do I get from here to here? And how do I get from here to here? And see if any edge is too much. Overwork, and we can do this. And in the end, like we assign the canonical paths from some really nice math procedure with some fractional matching, so it's doable. And that's what makes this paper long, but it's fine. So it's also just another method of bounding gaps by going from Hamiltonians with rules to Markov chains, and then using graph theoretical methods to bound the gaps of these Markov chains. And the trick that is used often is the projection number. So you have a big Hamiltonian that has its ground state subspace, has some gap, and has excited states. And now I will add a tiny bit to this. So how do I combine a huge and a tiny Hamiltonian? Then what happens to the spectrum of this guy is that like this bottom subspace kind of like splits up, and then these guys split up, and we can calculate that the small eigenvalues of the sum pretty much are as if you took the small Hamiltonian and restricted it to this ground state subspace of the big Hamiltonian. And this is a very useful thing that we use over and over again. So for example, like you take the full Hamiltonian, which has this part where the brackets need to move, and also where the brackets get created, and also the endpoints. Forget about the endpoints. Let's just go to this moving and creation. So let's pretend that the move part is huge and most important, and the creation is tiny. It really then means that your ground states are pretty much going to be uniform superpositions over things moving. And then a little bit of creation. So these uniform superpositions are going to be tied, but in a very tiny way. So these guys are ground states of H move, which are take two brackets and move them all around the place. Or take four brackets and move them all around the place. And now they can be connected in some ways, sometimes, by this creation and annihilation Hamiltonian. And that way, we have uniformly spread well-bracketed words. We have this guy that we know it's like the Heisenberg model, so the gap is like 1 over m squared. And then if I look at the whole Hamiltonian, I will know that the low spectrum will be just like the creation thing, restricted to these ground states which are uniform superpositions. And that lets me go from like Motzkin paths, which have plateaus, and like all kinds of different Motzkin paths where I move things around and it's the same mounting, but just like the plateaus have been shifted, to just walk on the Dick path, which is the path where the mountains don't have any plateaus. And these can be then transformed into, like when you read a mountain, you can also draw it as a tree. It's kind of like a go left, 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 right, right, left, right, right, left, right. Like going around a tree, you can read out a mountain. And then we have ways of growing trees and then assigning like how do you grow one tree from another tree. Because what we need now, these guys are a random walk of like mountains or trees, where a mountain, like you can either like dig down a hole and delete or erode a mountain, or you can actually create another mountain with an eruption of a volcano. So this is some graph that these different big paths are connected. We have the canonical paths method, and this can be difficult, especially when you have graphs like this. When you want to get from these guys to those guys, you have to go through the middle, and that means the middle edge is overworked, and then you're going to have something in here that's going to be, this is going to be very, very small, and this is going to have a very, very small gap. And this is going to be large because many paths have to go through the middle. So this is no good, but if the graph is connected, like you can go from here to here through many, many possible ways in the middle, the gap is going to be nice, and that's what we show. This is how the graphs look like. They have really nice symmetry, and you realize that it's somehow like have the word bracket in the brackets, or just a little bracket and the word outside of it, and it's kind of fun to play with. So we show that the gap is 1 over polynomial afterwards to this sequence. Okay. I told you that these models where I had a line and I had to say, I don't like this, I don't like this. So there were endpoints. So what happens if I make this chain like longer and longer and longer? The endpoints actually govern who's going to be the ground state. So I kind of want to get rid of this, and a natural way of getting rid of this is something that Shor came up with, and it's add a little perturbation where particles cost something. So it's a term that says like a delta left-left, or delta right-right. Now, this thing reserves the subspaces. So it doesn't join the subspaces. The subspaces stay invariant, but now it's going to add different costs to different subspaces. And the cost is going to come from the average number of brackets in a given state. So again, I can view it as, let's take my original Hamiltonian, whose ground state is the uniform superposition in each subspace. And now I add a tiny perturbation, which says, I raise the energy depending on the average number of brackets, average number of particles. And it turns out when you count the average number of particles in the all well-bracketed states, and you count the average number of particles in the one extra bracketed state, they are actually very close. The gap is like 1 over n. So it's also a fun calculation that's not trivial. I've been working on this like for several months and then realized that there's a section that Ramis has taken like that already F-noted. And maybe I have a different method, so I should not be so unhappy. And then this goes up and up. So by adding cost per particle, you can actually separate these subspaces from each other. And within each subspace, things are like frustration-free, just like what David was talking about. So there should be stuff about the gaps within each subspace. And the whole trickery of adding a cost is trying to take these subspaces that are now kind of equivalent and just pushing them up. And now there's no more cost per endpoints. So it's all about, imagine, that if the cost per particle was huge, then this would be bad, because of course the ground state would be all zeros. But the cost per particle is tiny, and the average number of particles in the say, well-bracketed state is like n over, or 2/3 n. But the cost is like 1 over n squared or something. It can be just something very small, but still enough to separate. So this is doable. And we have a unique ground state again, which is going to be very, very close to the uniform superposition over all well-bracketed states. So let's go to a gallery of models. What we have learned from this particular model that we can generalize, so we can come up with the new stuff. So I want to find Hamiltonians whose ground states have a lot of entanglement. So I would want to have a large superposition, but not too large, because you have a superposition over everything that's just a product state. So I want to have many, but not too many, significant Schmidt coefficients. So what I'll do, I'll try to come up with rules, transitions, projectors, or forbidden states, so that I have invariant subspaces that are connected somehow, connected components, and then I'll have to come up with a way of making the ground state unique so that I raise the energy of all of these subspaces. And this can be done sometimes by having like 1 or 2 local projectors, or it can be done by endpoint projectors, as we've seen in the Wreckage Model, or a tool that we have now just come up with, and it's very useful, is like looking at the average number of particles. That adds a little bit of frustration, but it's not too bad, and it's a useful thing. So let's look at the models that we have seen so far, or would like to see. So for the qubits, we had the Heisenberg model where the ground state could have been also the all zeros. It was boring. We had Heisenberg and pair creation where the different subspaces were connected, and these were running around, and again, like the Schmidt was kind of two, because it was either I have even number of particles or odd and all, and that's about it. In dimension 3, when I do QuICS, for a long, long time I thought that the most interesting thing were surfers. So surfers is like a surfer that's riding a domain wall, riding on a wave. And then you can have the surfer like go from left to right. But this was at a time when all that I could imagine was a linear sequence. But you've seen all the geometry of the subspaces that I showed you. It's nothing linear anymore, like what we do in the usual QMA constructions, like the state, and the next state, and the next state, and the next state. You can have all many ways to go. But the cool thing that it's all consistent. So surfers, then there's the AKLT model. That's also a Q-tree model, where the ground states are superpositions also of things like the pairs of particles A and B that can annihilate with each other, but you have also a -1 in the superposition depending on the parity of how the state has moved, and you also have like 2 to the number of pairs, or 1 over 2 to the number of pairs, I don't remember which one it is. So kind of like creating a pair actually costs you a half, something like that. And again, this is a typical model that has a Schmidt rank too, but can be viewed in our Now, there was the Wreckage Model. There was the cool thing where the delta, where the gap went like n to the minus beta, where beta, we believe it's 3. In practice, it's many. Or in the proof, it's many. And the entropy went like logarithm of that. So we have seen the big models where like D was 9 or 8 or something, where the entropy could go crazy and the gap was also something not too bad in these QMA constructions. So let's see where we can get here now. Still, for the Q-trits, I promised you the pair creation model with 2 types of brackets. So pair creation is a particle can be created as a pair, and a particle can move. So particles get created and disappear. Or can move and disappear again. So in this model, what if I have 2 species of particles? So X particle or a V particle or a diamond or a triangle can get created and they can move. So these guys move. A new pair gets created, and so on. What do you think are the invariant subspaces for this model? Sorry?
The ordering?
The ordering could be, or also like here in this part, everything can go down to 0. But you can imagine that you have like one extra particle, one extra red. Or you can have like an extra red and a white. Or you can have an extra red, white, and red. So there are the different subspaces that are labeled by some kind of irreducible strings. Irreducible strings. So there can be a thing like this that will never annihilate. The x's and b's are changing. And also like in a well-bracketed, or in a good subspace, when I cut it through the middle, you see that this part mirrors that part. Or if I had it here, then the irreducible string here would be this and this, and the irreducible string would be this and that. So the irreducible strings on the left and right kind of match and are mirrored. And when you count the Schmidt decomposition of a subspace that's connected to an empty state, it's like, again, 1 plus 8. The 2 and half is here from the length of the chain, and the 2 is from that I can have ABA or BAB. Those are the two only possibilities. And the question is also like how long the irreducible string is. And when you calculate things, again, the gap goes like n to the minus beta, and now the whole thing is more connected than the bracket model. Because for the brackets, like, they could only annihilate this way, or here they could also annihilate this way. So that makes it more connected and the gap gets nicer. So I actually believe that it's n to the minus 2, but again, like, we have to go through the proof, where again it just shows like 1 over n to the poly, and the entropy goes like log. So let's summarize here. The brackets and the perturbation model, they both are of this type, of log scale of entropy. And now we can go further. When you take the bracket model, and now you take, instead of just one type of bracket, you take 2 types of brackets. When you take 2 types of brackets, suddenly your subspaces get much more interesting. Because if you have a well-bracketed state, what's on the right side has like the green and the red bracket, and then green, green again, red, green. It has to match the other side. So it actually, the colors also matter. Not only how many extra there are. So you have an exponential number of them. It's not only like how many, but also what's their order. And that gives you, not really n, but square root of n, scaling of entropy. Because again, like then you have to calculate what the Schmidt coefficients are, and there are many of them, and the maximum Schmidt coefficient, and the most important one is somewhere like again is the square root of it, and how many of them there are, and the combinatorics and so on. It ends up something like square root of it, and when it gets better, when you're increasing the number of colors. So for this, you go and look at Peter Shor's QIP talk, or Ramis Movassag's talks, recent ones. So this is for 2 kinds of brackets. Now I'm going to do a similar thing than what I did here with pair creation, where I'm going to create 3 types of particles. So I have, or like even S species of particles. So here are things that they can move, disappear, move, disappear. And now I can have a different type of particle that can move, appear, move, appear, so on. So imagine that I have 3 types or more. Again, invariant subspaces are going to be irreducible strings where there's a string of letters where no 2 letters that follow each other are the same. So those are irreducible strings. And now, when you look at them, what they can be, suddenly if you have 3 letters, you can have an exponential number of them. So it's actually S for the first letter and S minus 1 for each next choice. Because all that you do for the next letter, you can choose whatever, just not the previous letter. So it's a nice exponential scale in there. And what we end up having is in the Schmidt decomposition, we have a nice exponential here. And then for the gap, again, it's going to be something that's like the length to the minus beta, and entropy that goes. I really believe it's, again, like a square root of it. And all then that you need to do is then add a little bit of cost. And again, just like in the bracket model previously, the lowest average number of particles is going to be in the subspace where there are no extra particles. So we're going to have a unique ground state, and it's going to be very entangled. And really, the left, kind of left irreducible string has to mirror the right. This is, for example, the geometry of the subspace of the good subspace with 3 species, but this is for small, and the graphs get nice when you go bigger. All right, so this really opens the door to all kinds of things. I'm not really going to talk about it, but if you want, you can instead of having different bracket types, you can use parity. That's my favorite trick. That like, depending on whether brackets get created here or here, they are different, and this kind of creates two species of brackets. All that you also need like the brackets to change color when they move. But you can do that. So there are models like that. I'm going to end up with all kinds of questions that we have from here. Because I have introduced this one new model, but I would like to have many more and understand what's the best thing. And I haven't found it yet. But I would want to find, can Q-tree chains, and specifically translation-free chains, and even more translation-invariant chains, hide something hard? So can I, from this type of Hamiltonians, where I rule out states, they create rules, they create subspaces, they can be entangled, can I hide something in it? So can I actually like give you a Hamiltonian? It will be hard for you to figure out what's going on. Hard for you to figure out the matrix product state itself. Can this be done for Q-trees? So now we know that for particular models, for four-dimensional particles, it's difficult, and for Q-trees, we know that matrix product state dimension is polynomial. So it already smells like NP, but I don't believe it's going to be. So we'll see. So I would want to find a promise code. The next thing, that all these models that I've shown you, they are somehow recognizable by a push-down automaton. All the states in there are something when you look at, like you read the letters from the left, and then you can unread them on the other side. So there's something like this in there. So maybe, would this be for Q-trees or something like connected instead of like the full QMA or MP, something smaller class related to some weaker computational model? I don't know. Like Tom already told me that like I probably like whatever happens, it might be a Turing model again. So we don't know. I would like to find out. What happens when the rules are what's happening in here? I was just creating pairs of particles. But what if I create a pairs of particles that already have string in them? So if I would really use like move singlets apart, would this give me any advantage or not? This is like in Sandy Ramis construction or the Movassagh construction. Or what happens if the states that I rule out are something more complicated, when it's just not just something minus one thing, but it's three things, just like in the AKLT model. And there are several ways of finding states that are orthogonal to this. It's not only AB goes to CD, but there's also a possibility of creating an AB pair from a 0, 0 and change the M. The next thing is when I have the cost per particle and the gap, this is changing the behavior of the model a lot. Because if I add a large cost, state stops being entangled. What's the best that I can tune things in? And again, like, what's the tuning of the gap and the entanglement? Adrian Fagreen from Northeastern has done some MRG calculations on this, and they are interesting. We'll see what comes out of this. Now, the big goal and the challenge is what's the best possible relationship between the entanglement entropy and the gap? And maybe we will hear something about this, like the area law, Mario Segevi's talk that's coming. So the best that we have seen in the Gottesman-Hastings model was something like this. We haven't quite achieved it, but we are something like -1/5 or something in our models. But is this really the best? Can it get better? So where the entropy would go like n, and the gap would go like 1/n? Would it be possible? We don't know. For some things, like what David has shown for his qubit models, there's an upper bound of 1/n on the gap, if the gap is closing. Would the gap in some of these more complicated models be closing like 1/√n? We don't know. Again, I'm trying to create subspaces that will be very much more connected so that the gaps will be bigger. We'll see. And then the combinatorics that we'll be learning about in these things do actually show up in other things. James Whitfield told me that like they show up in quantum chemistry spin eigenfunctions when you're calculating these Motzkin paths. Or also with Yudong Cao when we wrote the paper on perturbation gadgets, we also use these catalog and Motzkin numbers because like somehow if you have like a gadget and connect it to other states and you're making an effective interaction of these guys can get like flip, unflip, and you have to count the number of paths. This can happen. This is exactly the combinatorics that we've been doing. And then finally, Connor's matter people talk about the CFTs and what the models that we're doing, are they really related to something that they have seen already? And what happens if we generalize this to 2D? Specifically these pair creation methods, models that I think introduced. We'll see. And I'm curious what's going to happen. And this was the story. A very final speech. Thank you.
Thanks. We have time for 1 or 2 questions, and maybe Robin can start getting set up.
I got this image in my head while you were talking. I felt like you could take a computer science book and take this chapter on grammars and alphabets and use your ideas to do quantum energetics of grammars, general grammars and alphabets, well-formed sentences, etc. Is that interesting, or is it just a stupid image?
It's something that I like, and this is exactly why I have a computer science student, Movassagh, who's kind of looking at these things. But I would really like to understand the connections of the condensed matter models and the things that we have learned on in the theory of computation. And specifically things that are easier than the full power of computation. So like things like grammars. So what kind of things can be done up to local? Yes.
I'd like to add to that. Have you thought about basically using regular expressions to analyze what you have here, the equations among regular expressions? No need to go to a push-down automata. Go to something simpler. Looks like the structure is related to what's done in automata.
Okay, so the question is like, what if we use like regular expression, something weaker than the push-down automata, and analyze that? And we've done a little bit of this, but it seems that like the real interesting things happen only at these push-down things, where really like there's a lot on the left and a lot on the right that mirror each other.
Okay, thank you. And if there are more questions, you should find Daniel after the end of the session. So let's thank him again.